Okay, welcome back to lectures on engineering mathematics 2. So, this is lecture number 17 on Taylor's series. So, here we will discuss about what are the power series and radius of convergence of those series, and also then we will talk about the Taylor series and as a special case this Maclaurin series. Finally, we will go through some examples where we will construct a Taylor series. Okay, so what is the power series in the connection with the complex variable? So, a series of this form. So, we have a 0, then some constant again, and z minus z 0, another constant z minus z 0 square, or we can write down in a compact form. So, a n z minus z 0 power n goes from 0 to infinity, and this is called a power series in z minus a or z minus z 0 here. So, because this is all in powers of z minus z 0 with some constants. So, every term has some power of this z minus z 0. The first term is a constant term. So, we can think as a power 0. So, this is a power series, and every power series, this is the known fact that every power series there exists a non-negative real number r such that every z in this neighborhood z minus z 0 less than r, the series is absolutely convergent, and for z minus z 0 greater than r. So, outside this circle with center z 0 and radius r, the series is divergent. So, not convergent, and this number r is called the radius of convergence of this power series, and the circle here z minus z 0 is equal to r is called the radius of convergence. So, here in the context of the complex, it is same as what we have learnt for the real numbers, and no general statement can be made about the convergence of a power series on the circle of the convergence. So, here we are talking about that inside this circle the series will converge, and outside this circle with center z 0. So, inside the series will converge and outside the series will diverge, and on the circle we have no information that will depend on that particular case, where we have to check separately what is happening on this circle. But what we know about from knowing the radius of convergence, that inside the circle with radius r center z 0 the series converges, whereas outside this circle the series diverges. Okay, so, we also write that r is infinity. So, the radius of convergence is infinity if the series converges for all z, and we say that r is 0. So, the radius of convergence is 0 if the series converges only for z equal to z 0, because at z equal to z 0 all these terms will become 0, and definitely that series will converge, because that will have only this constant term. So, there is no worry about this, always this will converge, but in this case if the series converges only for this z 0, then we call that that the radius of convergence is 0, but if the series converges for all z, then we call that the radius of convergence is infinity. So, this was some preparation, and there are the formulas, developed formulas. We are not going through all these concepts, because actually finally we will see in Taylor series we do not need all these calculation of the radius of convergence, etc. There is another way of knowing that the region of this convergence or the radius of convergence. But for a general power series, the radius of convergence of such series can be calculated either by this so called the ratio formula, which is again parallel to what we have for real numbers, and there is another one, the root test, and then here from that root test we also get this the radius of convergence. So, either this whichever is convenient for a particular example, either we take this kind of ratio of the coefficients and then take the limit as n approaches to infinity, or we take this nth root and then take n approaches to infinity. In either way we can get this radius of convergence of a given power series. So, here if you want to find the radius of convergence, for instance, of this series z power n over factorial n. So, we will apply the first formula, that the radius of convergence we can get with the help of this ratio and then the limit, and we will readily see here that n approaches to infinity, this will go to 0, and so we have the radius of convergence for this series is infinity, which is also obvious if you take a close look at this series. This is nothing but the series of e power z, and as we know from the real numbers also that e power z, this is defined for any this argument z here. So, in the complex context also this e power z is very much defined. So, here this is defined for all z, and therefore, this radius of convergence is coming to be infinity. So, we can fix any z, this series will converge to just e power z. So, here the radius of convergence is infinity in this case. Well, so here for instance, if we want to find the radius of convergence of this series z power n and n approaches from 0 to infinity, sum is over n 0 to infinity. So, the radius of convergence, again we can apply this formula. So, here the coefficients are 1 1 for each term. So, we get just 1. So, that means the radius of convergence for this series is 1. So, if we talk about this point here z 0 is 0, and then this radius of this circle here is 1. So, outside this circle this diverges, and inside the circle this radius or say this series converges. This is what we know from the radius of convergence. So, that means for all z this less than 1, this series converges. This is what we know from this direct calculation of radius of convergence. We can indeed prove that this summation z n equal to 0 to infinity z power n is 1 over 1 minus z, which is naturally defined for z less than 1, where we have this is what we have seen already from the radius of convergence. So, to prove this, that the sum is equal to 1 over 1 minus z, we can think about taking the partial sum. This is one way we can prove this. So, we take the partial sum by introducing here the n minus 1. So, first n term we are considering and calling it S n. So, from this geometric series, so it is a sum of these geometric numbers. So, we can just get the formula we already know. So, it is 1 minus z power n and over this 1 minus z power n. So, here the remainder if we consider, that means this was the actual value 1 over 1 minus z, and then we have here 1 minus z power n over 1 minus z from this partial sum. So, this is the remainder term, and we will see that as n approaches to infinity, this remainder here will go to 0. That means, this is eventually the sum of the given series. So, here we have z power n over this 1 minus z, that is just after simplification of this one, and then what we observe, if we take the absolute value there. So, we have this absolute value of z power n and then 1 minus z, the absolute value, and here we can observe now that if this mod z is less than 1, if z lies inside the circle of center 0 and radius 1, in that case this will go to 0, but if this z is greater than 1, then this will not approach to 0. So, this error will grow indeed. So, this itself indicates here that this radius of convergence is 1, but we had the direct formula for the calculation of the radius of convergence, and here it shows that this if mod z is less than 1, this E n will go to 0 and as n approaches to infinity, but the condition is that when this modulus of z is less than 1. So, that is the condition which is again indicating us that this is the radius of convergence in this case is 1. So, coming back to the Taylor series, the main topic of this lecture, we will again relate everything to what we know already for functions of real variable, this Taylor series. Here it is a similar structure. So, the proof is rather involved. So, we will not go through the proof because, but otherwise it is analogous to what we have already studied for the functions of real variables. So, here f z is analytic inside and on a simple closed curve. So, this analyticity plays very important role in this complex analysis. So, now again this f z is analytic inside and on a simple closed curve C, and then we take 2 points z 0 and z 0 plus h, maybe in the neighborhood of this z 0, the 2 point inside again the C. So, where the function is analytic. Then we have this expansion that the value of f at z 0 plus this h could be a complex number of course. So, this can be written as f z 0 h, the first derivative of f h square by 2, the second derivative of the f prime, and so on. So, this is the Taylor series which we know from the real analysis as well, or we can write in this form. So, f z can be written as f z naught and f prime z naught z minus z naught, again the nth derivative z minus z naught power n, and we can continue with this expansion. So, this is similar to the Taylor series from the calculus which we have studied already in engineering mathematics 1 for functions of real variables. In this case, the difference is that we know the formula already from the previous lecture, that the derivative of this complex functions can be calculated with the help of such integrals which we have just seen in previous lecture. So, the nth derivative is given by factorial n 2 pi I and this f z over z minus z 0 power n d z, with counterclockwise integration around a simple closed path C that contains z 0 in it. So, in practice one tries to avoid computing this integral because computing these integrals may not be easier. So, we will see the practical approach, that how we can avoid computing indeed these derivatives itself which are appearing here in these Taylor series. So, concerning this C here, that can be any curve inside this around this simple closed path that contains z 0. So, containing this z naught point, we can take actually any simple closed path and this integration can be done. Okay, so, if z equal to 0, this series, this Taylor series is called the Maclaurin series, that is another name of this Taylor series for z equal to 0. So, we can also rewrite this Taylor series, or in some literature you will find in this way, that suppose this f is analytic in this z minus z 0 less than r naught. So, here we have this disk with the radius r naught, and then f z has the power series representation. So, f z we can naturally write in this as a n and z minus z naught power n, and then a n we can define as the nth order derivative at z 0 divided by factorial n. So, it is the same series what we have seen on previous slide, but just written in a slightly different form. And the Taylor series converges here to f z for z that lies inside the disk z minus z 0 less than equal to r naught. So, what we learn here, that where if our function is analytic in this region here with center z naught, and then we have this radius which is denoted here by r naught. So, as far we can go as long as we are in the region of this analyticity, and this Taylor series will converge for all z we take in this region. So, in the next lecture we will observe that as soon as we find a point here where the function is not analytic, we cannot go beyond this, we cannot cross that point, because the condition here is that f z has to be analytic inside that disk here with radius r naught. So, the whole region should not have any point where the function is not analytic. So, that we will discuss a bit more in detail in the next lecture indeed. Now, some remarks. So, the any function which is analytic at a point z0 must have a Taylor series about z naught. So, that is also important, that suppose we know that the function is analytic at a point, we have no other information of the region of analyticity. So, but we can write down its Taylor series, because when we know that the function is analytic at a point z naught, there must be some neighborhood z minus z naught less than epsilon. Epsilon could be very small, but analyticity ensures that there will be a neighborhood where the function will be differentiable or it will be analytic. So, just knowing that the function is analytic at a point z naught, we can write the Taylor series. However, the radius of convergence, which is epsilon, could be very small depending on how far we can extend this region of analyticity without having a point where the function is not analytic. Okay, so, the remark 2, if f is entire function, that means it is analytic everywhere, then the radius of convergence can be chosen arbitrarily large, or meaning that radius of convergence will be infinity. In that case, if we know that the function is analytic everywhere, there is no point where the analyticity breakdown. For instance, we have the exponential z e power z. So, this exponential z is analytic everywhere, and then we can write down its Taylor series, which must be valid for all z. Okay, so, another remark, that when it is known that f is analytic everywhere inside a circle centered at z0, the convergence of the series is guaranteed within the circle and no test of convergence is required. So, indeed we do not have to test the convergence for this series, that is already a proven fact, that if we are in the region where f z is analytic, then we do not have to prove the convergence of the series will definitely converge as long as this whole region, the disk inside this radius r, the part of the circle inside the radius r, if the function is analytic, then definitely the series will converge. The series converges to f z within the circle about z0, whose radius is the distance z naught to the nearest z1 at which f fails to be analytic. So, this is the point which I tried to explain in previous slide. So, if we are at this, let us say we have z0 here, and then we can go as long as we are covering the region of analyticity. If your function is analytic in this whole domain, so the series will definitely converge in that domain, but we should not cross a point. For instance, there is a point here z naught where the series, where the function is not analytic. So, we can at most go to very close to this z naught, but we should not touch that sorry z1. So, we should not cross or touch this z1, and then there is no problem about this convergence of the Taylor series where our function is analytic everywhere in this disk. And this is what we can absolutely get the radius of convergence by knowing that how much we can extend this disk, so that no such point comes into it where the function become non-analytic. Okay, so, find the Taylor series about this z equal to 0 of this function. For instance, we are taking here 1 over 1 minus z. So, this function plays a very important role, and we will see in a minute that why it is very crucial to expand this function first in Taylor series, and then we will actually utilize this function, or we will use this function, the series of this function, to write the Taylor series of many other functions. So, to get the series of this function, we can Taylor series, we can get the first derivative, which is minus, so the plus indeed. So, it is 1 minus z. So, you have 1 over 1 minus z is square, and we can get at 0, the value is 1. We can get the double derivative, which is 2 over 1 minus z cube, and again this derivative at 0 will be just 2. So, the third derivative we will get 2 into 3 divided by 1 minus z power 4. So, the third derivative at 0 is just the factorial 3. The nth derivative at 0 is factorial n, and this f z we can write down as 1 plus z square z cube and so on to this z power n, and here the, or we can write in the compact form that f z is n 0 to infinity z power n. So, this is a very important series, as I mentioned before, that this 1 over 1 minus z, which the expansion is 1 plus z square z cube and so on. It is we are going to use this series for getting many other Taylor series. Coming to the radius of convergence for this series, we can use for instance this formula, and immediately we can get 1. So, this is one way of getting the radius of such power series, or which we have discussed, that we are talking about, we are expanding this around z equal to 0. So, how long we can go to define this region where the series will converge is the point where exactly the analyticity will break. So, here if we have this z equal to 1 point where the analyticity breaks down. So, we can go up to this point, we should not cross or touch this point, and then this circle here of radius 1 will be, so the 1 will be the radius of convergence from the direct observation of the function regarding this region of analyticity, but the same we can get also by the formula. So, is that now, I hope it is clear now that in either way we can discuss the radius of convergence. So, for instance, if we take the Taylor series of this function z plus 2 over 1 minus z square, and about this z equal to 0, we want to get this Taylor series. So, there are two ways, of course. One, we can use that standard formula, but there we need to get the first derivative, we need to get the second derivative, evaluate them at 0, then third derivative and so on. The process will be complicated if we have a complicated function, or even more complicated than this one. So, the trick is here that we will try to break our function in terms of the function which we have just studied before, that was 1 over 1 minus z. So, just to note again here that not only for 1 over 1 plus z, 1 minus z, we can also write down for 1 plus z, for instance. That will be having the similar structure, but the sign will change there. So, we will have n 0 to 1, and then, so here the minus sign will come. So, we will have minus 1 power n and this z power n. So, we will have the series for the 1 over 1 plus z as well, not only for just 1 minus z. So, there 1 minus 1 power n will come as an extra term, but and the radius of convergence will be same again as here it is 1. So, these two series, the 1 over 1 plus z and 1 over 1 minus z, these two will play a very crucial role, and we will see in the next slide. So, we have this we want to get the Taylor series of z plus 2 over z 1 minus z square. So, what we will do, we will use this idea of the partial fractions, and that is what we will do in most of the examples. So, this z plus 2 over 1 minus z square, if we break into the partial fractions, we will get these two terms. One is 1 minus z and another is 1 plus z. So, now we can expand each of these partial fraction in a Taylor series. That means, this z plus 2 over 1 minus z square, we can write down 3 by 2 and the Taylor series of 1 minus z. So, we have these power z power n, and for the series of 1 over 1 plus z, this is minus 1 power n z power n. So, these two series, which both of them are valid in this region z minus 1, the disk radius 1, or we can just simplify a bit here. So, we will get this 2 plus z 2 z square plus z cube. So, this is another series here we got for z plus 2 over 1 minus z square, which is valid in absolute value z less than 1. Okay, so if we want to get the Taylor series of 1 over z minus 2 and z minus 3, that is the product there, we will use the same trick again. So, here we can do the partial fractions. So, these partial fractions of 1 over z minus 2 z minus 3 will be 1 over z minus 3 and minus 1 over z minus 2. So, but we know the series of 1 minus z or 1 plus, we know already the series of 1 minus z or 1 plus z. So, we will modify these partial fractions in this form, so that we get something 1 over plus minus and then some z. So, we can expand this each in the Taylor series, because the first one we can write down as taking here minus 3 common, and then we have here 1 minus and then z over 3. The second term what we can do, we can take minus 2 common there, and we will have again here 1 minus z by 2 from there. So, now we have 1 minus some constant z, here also we have 1 minus, instead of z now we have z by 2, here instead of z we have z by 3. So, in this series we will just replace z by 2, and in the second case z will be replaced by z by 2. So, this is exactly the series expansion for 1 over z minus 3. So, we have replaced z by z minus 3 in this expansion there, and here z is replaced by z by 2, otherwise we have the same series. Now, but the convergence will change, because in this case the convergence was when mod z is less than 1, but we do not have this z, instead of z we have z by 3 and z by 2. So, accordingly this series will be valid for absolute value z less than 3, because here we have the condition now that the z by 3 should be less than 1, that means the mod z should be less than 3. So, this will be the region for this first series to get convergence, and for the second one accordingly we can get from this z by 2 less than 1, we can get that this absolute value z is less than 2. So, from there we can get this convergence for the second series, and what we observe that we can combine these two, and now the validity we have to check, because we are talking about that this is our series. The first one was valid when absolute value z less than 3, the second was valid here in the disk radius 2. So, as combined here, as both the series are valid in this disk less than 2 radius 2. So, this is the validity now for the whole series, because the individual series here, this is valid for mod z less than 3, this is mod z less than 2. So, as a whole we have to see the common region which is coming now, the absolute value of z less than 2. The last example here we will be talking about the Maclaurin series of 1 over z plus this 3i. The same trick we can use again what we have done before. So, 1 over z plus this 3i. So, we take this 3i common there to have this form 1 minus or 1 plus z by something there. So, if we can expand this again, instead of taking z there, we will take z over 3i, and the validity will come from this condition that absolute value z over 3i should be less than 1, that means this z less than 3. So, that will be the condition for the validity of this series, and then we can expand it with that standard series. So, minus 1 power n and 3i power n and z power n. So, which can be just written in this form, or we can expand it, we will get such terms out of this series there. So, what we have seen with the help of that two particular, I mean in particular those two series, we can utilize that for the expansion of many other functions, and the more we will discuss of course in the next lecture, where we will generalize the idea of this Maclaurin or the Taylor's series. So, these are the references we have used for preparing the lecture, and just to conclude that we have learnt now the Taylor series for f z, the complex functions, and that is the similar expansion what we have for the real functions as well. And regarding the interesting fact about the convergence, we have seen that the series will converge, we can go to the maximum radius around this z point as long as it does not have any point where the analyticity breakdown for the function z. So, for instance, if we assume that z1 is the point where the function is not analytic, then we can just go up to this z1 maximum to have the validity of the Taylor series or the region of convergence or the radius of convergence for this such Taylor series will be that radius r. Okay, so and we have seen that practical method for obtaining Taylor series, because that is very useful. We do not have to expand and get all these derivatives for many functions, and this the expansion of either 1 minus z or 1 plus z was very much useful, and we have seen in several examples how we can use this series to expand many other functions. Okay, so that is all for this lecture, and I thank you for your attention.